Let's derive GouyChapman theory. So remember, we have a charged surface and we have a distance from that charged surface h, and we want to see how the surface potential changes, or how the potential changes as we move away from that surface. So we've got the surface potential, which we call phi naught, and the real question is, how does phi change, how does the voltage change as we go away from that surface? Does it die off like this, or maybe like this? Or is it linear? That's the real question. How does the potential change as we move away from that surface? And to solve this, we're going to use Gauss's law. And Gauss's law tells us basically the second derivative of voltage as a function of distance is going to be a function of the charges that are there to neutralize it. So specifically the charge density. So the charge density rho is basically the total amount of charges per cubic meter. So we'll just write charge density here. Okay, so we have to come up with an expression for charge density. So charge density, we can just add up all the charges, so it's just a sum. So we're going to go over all the different ions that are available to us, and each one is going to have a specific concentration. And remember, we're doing a numerical concentration here, the number of ions per square meter. And each ion is also going to have a charge, which is the unit charge on it, is it 1, 2, or 3, multiplied by the charge on an electron. So that would give the actual charge. So we sum that up, we have the charge density. So we can just put that into our expression for Gauss's law. So the second derivative of the potential with distance from the surface is just going to be the negative of this sum, the numerical charge density, the charge on each ion, divided by the permittivity of free space and the dielectric constant. Now the problem with this is that the concentration of ions changes as we go away from the interface. So if we look at a graph of concentration of ions, we know that we're not going to have a lot of co-ions near the interface. And so we might see a graph of ion concentration like that for the co-ions. So next to the interface, there's not that many of the co-ions. On the other hand, we expect that the concentration of counter-ions is actually high near that surface. So what that tells us is that C, the concentration of a particular ion, is going to be a function of distance. And so we've got to remember that this is not a constant. So we're going to have to come up with an expression for that. Well, fortunately, we already have an expression for that. Remember, we said that the concentration of any particular ion is a Boltzmann weighted average of its energy. So we can say the concentration of any particular ion. So the concentration of an ion near the interface is equal to the concentration far from the interface times this exponential. So notice if we have a positive potential and a positive charge, this is overall going to be a negative exponential, which tells you that your concentration is less than it would be. Okay, so if you're a co-ion, your concentration is less, as indicated up here, and if you're a counter-ion, your concentration near the interface is more. Let me label these axes. This is H, and this would be concentration in both of these graphs. Okay, so all we have to do now is put this expression for the ion concentration in here, and then solve the differential equation. So let's write that out. Okay, so we have a differential equation where we have the second derivative of the potential with respect to distance from the interface. And over here we have concentration, but notice concentration is a constant. It's not going to be, this is not a real variable. So the only variables we have are over here, which is the surface potential. So notice we have surface potential here, we have the derivative over here, which means this is a differential equation. So we'll look at a way we can make this into a simpler differential equation in the next screencast.